Hello, space fans. Welcome to another edition of Space Fan News Live, which is not really Space Fan News Live. We're not going to be talking about this week's episode, though it is up, and I do recommend you check it out. Today, or this morning for me, this evening for Katie and Paul, we'll be talking about the supermassive black hole at the center of our galaxy. So, as always, I'm your host, Scott Lewis. With me tonight is the amazing astrophysicist, Katie Mack. How are you doing, Katie?
Hello. Good to be here.
And we're joined by, well, Sagittarius, or Paul, once he puts his camera back on. And you can say hi to everyone. Hey, Paul, how you doing?
Hello.
So Paul's one of our astronomers that typically joins us in the virtual star party from New Zealand, and I asked him specifically for this show to bring in some views of what we're talking about. So we're going to be talking about the supermassive black hole at the center of our galaxy, which is known as Sagittarius A star. But before we get into that, I do want to go over a few things on how you can interact with us. So I have the Q&A app turned on, so actually you should load that up because that might help. And also so you can use that here on YouTube or Google+. Also anywhere in the comments, both on YouTube or Google+, and we are all on Twitter. I know of my Twitter handle down here. I'm Scientific Scott. Katie is Astro Katie, and if you don't follow her on Twitter, you should, regardless of what you feel about this show. She's awesome on Twitter. And we have Paul, who's UpsideDownAstronomer.com, but you're what? You're Astro Stew on Twitter, right?
This one.
There we go. So I will get everything going up here, but Paul, you had your image up, and I'm going to screen share real quick the big area that we're talking about here, and then I'm going to have you pull up your screen and show us exactly what we're looking at. So right here, just got Photoshop open, and we're looking at the big band of light going on here with our Milky Way. And so Sagittarius is going to be looking down dead center, and Paul, yep, there it is. So X marks the spot. This is what we're talking about when we look up in the night sky and are looking for Sagittarius A star. So we're looking at the area. We can't really see it, and we'll get into why we can't see it, but we're looking at Sagittarius A star, the supermassive black hole. So with that, Katie, what's with this? What's with a supermassive black hole as opposed to a black hole? What's so special about them? Why do we have them at the center of the galaxy as opposed to flying around all over the place? What's going on with that?
Well, so we think that pretty much every galaxy we've looked at has a supermassive black hole in the center. And when we say supermassive, all we mean is really, really massive. So that's usually about a million times the mass of the sun. Our supermassive black hole is about 4 million times the mass of the sun. It's in the center of our galaxy, and basically we think that when galaxies are forming, the black holes at the centers of the galaxies form at the same time as the galaxies in some kind of simultaneous process where as the galaxy builds up mass, the black hole builds up mass, and they sort of grow together. And most galaxies have one at the center. Some have binary black holes at the center. So
nice.
As time goes on, galaxies come together through gravitational attraction, and they merge and do this sort of spirally thing, and the black holes spiral in together. And sometimes we've caught galaxies where there's a binary black hole where they haven't quite spiraled in together yet.
So do those do anything different as far as if they are spiraling, or are we seeing different geometries going on as far as the formation of this galaxy or the way things move and orbit it?
Well, black holes are pretty small in terms of their sort of physical size. So it's really just the very, very center of the galaxy that's affected by what's going on with the black hole itself. In some galaxies, the black holes are active and doing much more exciting things than our black hole is doing. and then they can have really far-reaching consequences. So there are some black holes that are actively eating things in their surroundings. So they're pulling in gas and dust and stars and planets and things like that. And when that's happening, they get disks around them of glowing hot gas, and they shoot out jets from the pole.
So essentially, they're burping.
Well, no, I mean
No?
these things are like some of these are sort of constantly shooting out huge jets of energetic material. So they're not just they're not always
not just when consuming stuff. They're just constantly just tearing stuff out and sending into space.
So these things are called active galactic nuclei, also known as quasars in some cases, or radio galaxies, depending on what sort of configuration they're in. And these things can have, they can be the brightest sources in the universe. We can see them from the brightest consistent sources, things that go on for a while. We can see these things from billions of light years away, because they're just so bright with these jets and with these accretion disks that are glowing. Now, our black hole isn't doing so much of that. It's pretty quiet, although it is about to eat some gas. There's a gas cloud that's spiraling into the black hole right now. It's called G2, and we're watching it, and we're going to see something happen to it really soon.
Yeah. Actually, there was a question we had on here. I was looking at it earlier. I believe it was Craig Landon. It was, who or where do we watch for news and information regarding that large cloud of gas that's said to be headed or meandering towards Sagittarius star? Is there a particular outlet or institution that's already begun measurements on it?
Well, I think for a lot of these things, NASA is going to be pretty up to date. But lots of people are watching this thing. There are a couple of groups around the world that like to observe the galactic center specifically. Mm-hmm. So there's a group at UCLA that has a galactic center group, and they use things like the Keck telescope to really examine that center region very closely. And there are other telescopes around the world. There's a telescope in Chile called the Very Large Telescope. So
is it large or is it?
It's large, yeah.
Yeah.
Astronomers aren't always very creative about
naming. I know. I'm loving how they're coming out with them though, like the super mega ultra large telescope.
Yeah. So that's like an 8. It's actually a few telescopes together, but they're like 8-meter diameter telescopes. Anyway, so there are a couple of telescopes around the world that are really actively watching this. The Galactic Center group, and so the groups in there are telescopes based in Chile that look at the Galactic Center because you can't actually see the Galactic Center from the northern hemisphere. You have to be either close to the equator or in the south to see the Galactic Center, because the way that our Earth is tilted, the north is tilted away from the center of the galaxy, and the south is tilted toward the center of the galaxy. So when you're in the northern hemisphere and you look up, everything's sort of orbiting, everything sort of spins around the North Star, Polaris. And if you're in the south,
like wistfully looking out into the rest of the universe, and the southern hemisphere tends to be staring down, like, what are you doing down there, galaxy?
Yeah. So down here in the southern hemisphere, I'm in Australia. We have a much better view of the galaxy.
You do. I'm so jealous of your skies.
Our sky is so much cooler than your sky. Because we've got the Galactic Center, and we've got 2 satellite galaxies. We've got the Large and Small Magellanic Clouds. So we've got tons of stuff going on, and because we're looking toward the center of the galaxy, we're looking toward more stuff. More stars and more clouds of gas and everything, right? So we have just much more sort of populated sky in terms of stars.
Well, Paul, do you have any? I know you were doing some images right now. You said of the tarantula, but do you have any images of the large and small Magellanic Clouds, these satellite galaxies that Katie was talking about?
Not in total. My field of view is too small to pick up those galaxies, so you pick up bits and pieces of them.
I meant more like saved that we can take a look at.
Yeah, same. I haven't imaged them because I can't actually take the full picture.
Oh, okay. Well, then we'll look for some later and put them on. Or maybe that's a challenge. I'm always challenging Gary to do the full North American nebula. Maybe I can challenge you to do some bigger composites. Because I'm always challenging you guys.
Yep.
All right, so I'm going to do a quick break to take a look at the questions that are coming in here. Before we dig a little bit deeper, I did want to show this image too that we're sharing for the UCLA page. This is just showing. I know that you and I were talking about this earlier, Katie. So is this kind of what you're talking about? These are Fermi bubbles, so we're talking about something a little bit different here. But as far as these jets shooting out, is that what you were talking about?
Yeah, so this is a really interesting. So this I should say is an artist's representation of
Right.
Some data that we have, and it doesn't look anywhere near that clean in the data. But basically, if you look at the galactic center with gamma rays, you see these sort of bubble shapes jutting in and out of, jutting above and below the galactic plane. And if you look really closely, you see what looks like jets coming out of that, out from the center of the galaxy, and those pretty much have to be remnants of a previous outburst of the galactic center black hole. So some point in the past, it looks like the Sagittarius A star, the galactic center black hole, was eating something and had this jet shooting out of it. We don't see any jets active today, but it looks like there was something in the past. So we see this, what looks like this jet feature and these bubbles, and we still don't know what the bubbles are made from. So there are theories that they have something to do with an outburst from the galactic center black hole, which is a very plausible possibility, or it's also thought that they could be from a burst of star formation in the past. And we don't know at the moment which of those things it is, but there seem to be these big bubbles blown out, and we've seen in other galaxies big bubbles blown by black holes. So as a black hole is eating things, I mean, the black hole itself can't put anything out, right? The black hole itself just pulls things in. But if a black hole is actively accreting, actively pulling matter in, then it's just the gravitational pull is so strong really close to the black hole, and it stirs things up so much that you get these incredibly bright sources of X-rays from that accretion disk as things are falling in, and you also get the magnetic fields getting all twisted around, and as the magnetic fields are getting twisted around, it accelerates these jets of particles, these hugely energetic jets of particles. So all of that can do a lot to the sort of nearby, intergalactic medium, or the galactic sort of surroundings. It can all blow these bubbles, it can make these huge jets, and these glowing radio lobes that we see in some active galaxies. So we think that maybe our black hole was doing something really exciting like that in the past, but at the moment it seems to be.
Now it's kind of boring. It's like, well,
it's not boring. I mean, it is about to eat something, so that's exciting.
Well, before we get into the eating part, I do want you didn't bring something up, so I do want to share this comment here on YouTube that Katie Stocco put out there. It's got Katie, a question I've wanted to know the answer to forever. Why has black holes been portrayed as a whirlpool-type looking object in some videos about the universe? I thought they were spherical. Katie, what are your views on Hawking's theory that when black holes evaporate, they take all the matter with them? So it sounds like it's two questions. You touched on the first part of it, which was about, you're talking about the accretion, or about the stuff sucking in and moving towards it, and just because of the way that everything works in the universe, with the angular momentum happening, it's going to start swirling. Yeah. So they're more spherical. They're not these whirlpools of everything.
So the black hole itself is spherical, unless it's spinning, which it probably is. And if it's spinning, then it's probably a little bit oblate, so like bulged out at the equator, like the Earth is. Mm-hmm. So if it's spinning, it's a little bit oblate, but it's basically a spherical-ish kind of thing. But the matter falling into it makes a disk, just like everything in the universe, because of its angular momentum, forms disks when it's sort of orbiting. So you take something that's orbiting in a sort of random 3D kind of motions, it always collapses into a disk. Right. It has the ability to interact with itself.
And that's just because it's easier. It just conserves all of it. It's not because it's not like the law of pancakes, that universally accepted. You know, we love pancakes more than anything else, so we're always going to be disks.
Well, there's a really great Minute Physics video about this if you ever want to look that up. But basically, what's happening is you have a whole bunch of random motions. There's all sorts of directions, but there's like a net angular momentum. If you add up all those random motions, there's a net angular momentum of everything kind of en masse moving this way. And so the things moving in and out of the plane kind of cancel out, and they bump into each other and they flatten out, and so everything flattens into a disk eventually. Now this doesn't happen for dark matter, but that's a totally different topic. But for every regular kind of matter,
dark matter, I mean, even though what's that? We'll be having more of these, and dark matter is something I know that is very near and dear to Katie's heart, and we will be digging into dark matter in weeks to come.
So anyway, so the reason that black holes are usually portrayed as whirlpools, things falling in, is because we can't really visualize everything kind of falling in every direction.
Right.
But if you approach the black hole from any direction, you will fall into it if you get past the event horizon. And so when usually we use a visualization of black holes where it's like you have like a rubber sheet and you drop something in the middle and it makes this dent. And that's like a 2D representation of a 3D.
Right, because the sheet's a plane, and so it's 2 dimensions there. I mean, it'd be like, okay, you're holding this marble in your hand, and you're simultaneously looking at it from every single direction, and then trying to visualize that.
Yeah.
In a video, you just can't. That's.
I mean, yeah, because it's all about like the curvature of space-time, and we can visualize that by drawing a curved 2D surface. We can't really draw a curved 3D surface.
Right. And then looking at it from outside that third dimension.
Yeah, it's really hard to visualize. So yes, black holes are 3-dimensional. The disks are kind of roughly flat when things are falling in, but you can fall into a black hole from any direction.
Right.
And there are 3D things. What was the other part of that question? Something about things not.
While I pull that back up here, I'm going to show Paul's amazing image. What are we looking at, Paul?
This is part of the small Magellanic Cloud. I can't get it all into the same image, but that's should be the centre part of it.
So are those supernova remnants that we see? Those little clouds?
Will be nebulous regions in the cloud somewhere.
Mm-hmm.
I see. This is from again Katie Stokos, and Katie, what are your views on Hawking's theory that when black holes evaporate, they take all the matter with them?
Right. So this could be a long topic to get into, but
should we use this as a follow-up? Like we can just talk about that, because I did ask for people to give us topics that we will talk about later on. So maybe, Katie, I will write that down. Katie Stoko, I will write that down, and we will follow up on that specific theory itself, because it sounds like it's something we can go into much more than a half hour for easily. Just the look on Astro Katie's face, like, oh nope, we're going to talk about this for a while. So.
Yeah, I mean, the brief version is that there are a couple of different ideas about what happens to the stuff that goes into black holes, and Hawking's original idea is that stuff goes in, but then the black hole eventually evaporates and just radiates pure heat energy, and so you lose information. And there are new ideas now that maybe that information, stuff that falls in, the record of what fell in gets recorded somehow and emitted in some other way, and so that information is not lost.
Right.
And
that gets into, like, we have to define what we mean by information and what that means on this scale, like because it's not we're using terminology now that has a different meaning.
Yeah. I mean, you can, for this purpose, you can say information just is the record of what fell in. So if I drop a toaster into a black hole, or if I drop a bowling ball, or if I drop
all your toaster atoms. Gotcha.
You won't be able to tell the difference at the end when the black hole evaporates. You won't know what went into it. If it's this sort of typical Hawking radiation kind of idea, you'll have no way of distinguishing what you threw in. You just know that you threw in a certain amount of mass, and that means that a certain amount of energy is radiated at the end. But yeah, anyway, it's a long topic.
Definitely get into it. Let's see here. Yep, I'm seeing another one about that cloud of gas. So yeah, what is going on with that cloud of gas heading towards the center? And what are we? Do we have any hypotheses of what we're expecting to see?
Well, we expect to see a little bit of a flare up in X-rays, I think. So it's so the I mean, stuff falls into the black hole. Little bits of stuff fall in. We actually see Sagittarius A star as a kind of variable X-ray source. So it is, there's kind of stuff moving around there. But when something falls in, we'll expect that basically as it's falling in, it's going to heat up as it's sort of spiraling in and collide with itself. And so we'll see sort of a flare of X-rays and optical light. And, we don't know exactly what it'll look like because we've never seen this before. Mm-hmm. So it's going to be pretty exciting. And I think it's kind of just it's already falling into the point where we see that it's starting to stretch out, and this is a process called spaghettification.
Spaghettification, yeah.
Being stretched out into spaghetti by the tidal forces of the black hole. So as you're falling into a black hole, the part of you that's falling in first is feeling a lot more gravity than the part of you that's falling in later, and so that gravity differential stretches you out. And so that's called spaghettification, and we see that happening already with this cloud of gas.
That's awesome.
Black hole. So that's cool. So yeah, we're just gonna watch it fall in.
It's just like, yeah, we're just gonna watch you being stretched and ripped apart, cloud of gas.
Yeah.
Thank you for sacrificing yourself for science.
Sorry?
I said thank you for sacrificing yourself for science, cloud of gas. We're just gonna sit here and watch you. Do we Do we know about when we're going to start seeing the majority of this matter go into it?
I'm not sure. I mean, it's kind of happening about now. I mean, it's starting to go in now. But the whole cloud is, I think it's like 3 times the mass of the Earth. So it's a pretty massive cloud of gas. And it's just kind of getting there now. So we should start getting cool data from it really soon. And I haven't been able to find exact timescales on it, but
okay. Well, speaking about sizes here, we're asked a question on the Q&A app. Roughly, how small is the black hole in our galaxy? So we were talking about this a little bit earlier for the show.
Yeah. So we measure the size of a black hole by the event horizon, which is the Schwarzschild radius, and that's the point of no return. So
right.
I mean, the black hole is basically infinitesimally small in the sense of there's, you can define it by the sort of singularity at the center where everything comes to a point. But usually we use the event horizon because that's the point where we can't see anything beyond that. So we have no idea what's happening to something after it goes through the event horizon. And for our galactic center black hole, that size is about 11 million kilometers. So it's like
small. That's so tiny that I was expecting something enormous. And
yeah, it's really small. So
you did the calculation to light seconds. How many light seconds is that?
40 light seconds. So for comparison, the sun is about 8 light minutes away.
Right.
So it takes 8 minutes for light to get between us and the sun. The radius of the black hole at the center of the galaxy is only 40 light seconds. So it's pretty small.
Like from the Earth to the moon is about 1 light second. So imagine 40 times that, and that is, wow, that's so small for this supermassive black hole.
Yeah. It's small. But if we had a black hole the size of our sun, like the mass of our sun, and there are tons of black holes the mass of our sun out there, as massive stars collapse down and become black holes when they die, that would have. So if our sun became a black hole right now and just collapsed on itself, its Schwarzschild radius would be about 3 kilometers.
Yeah. Pretty small.
So it would be. Yeah.
So
like these things are.
LA is much larger than that Schwarzschild radius.
Yeah. So black holes are not big objects, They're pretty small. And the way you define a black hole is really by that compactness. So by having all of its mass. So anything that has all of its mass within its Schwarzschild radius is a black hole. So basically, if you take the sun and if you can get all of that mass into that source gel radius, into that 3-kilometer radius, it will be a black hole. Like
because essentially the light can't escape it anyway, right?
Yeah. So that's the point at which the escape velocity, the speed you'd have to be going to get away from it, is faster than the speed of light. If you can get all that mass into that space, then it becomes a black hole. And so, in general, if you take any large amount of mass and you squish it into that space, then it'll be a black hole. So, like, if you want to become a black hole,
I do actually. You read my mind.
All you need to do is curl up into a little ball about the size of a nucleus of an atom, and then, the size of. Sorry, no, it's smaller than that. It's a millionth the size of a proton, I think. You have to be pretty small. You have to
so I need to be crying really, really hard, wrapped up, and just keep shrinking down on myself.
Yeah, there are moments when you feel that small. Anyway,
right.
You know, you just kind of squeeze in there, and then you would be a black hole. So anything, if it's small enough, if it gets compact enough, could become a black hole. It's just that it's very hard to do that in general, because
how do I take all of my atoms and squish it into the space tinier than an atom?
Well, you would need like a really, really strong force, and that's what this gravitational collapse gives you with ordinary black holes or with supermassive black holes. If you get enough gravitational energy in there, get enough stuff, that makes it so it can't support itself. So usually with a star, what happens is you have a star that's kind of held up by its nuclear reactions, and it's kind of puffed out by that heat. Right. But if it runs out of fuel, then it can't hold itself up anymore, and it starts to collapse. And it goes through various stages where different kinds of like nuclear forces are holding it up, and then eventually there's nothing strong enough to counteract all that gravity. So you have enough mass in this small enough space, nothing can stop it from collapsing. It'll inexorably collapse into that space. And so gravity is amazingly good at collapsing things down and making black holes by just getting everything into that tiny, tight space.
Right. Well, I'm going to risk feeding the trolls here, but I'm going to put a question up here. This is from Mike Mueller, saying that black holes are not confirmed. Let's don't forget this.
Oh, okay. So I would say they're pretty darn confirmed.
Okay.
Okay. So there are a few places in the universe where we're pretty sure we see black holes. Things like stellar black holes, where there's a sort of solar mass-ish black hole with another star orbiting it, and we see it eating that other star. We see it pulling that material in, and we see that star moving around really close around an object we can't see, and that gives us pretty good indication there's a black hole there. But for the black hole at the center of our galaxy, we have extraordinarily good data. So the things that we've seen for the black hole around in our center of our galaxy basically indicate that there is so much mass in such a small space it can't be anything else but a black hole. So we see stars orbiting around that central spot, and the orbits of those stars get so close to that central point, and they go so fast that we can measure the mass of that thing, and we can measure the size by how close those stars are getting, and we see that it's just far too compact to be any other kind of object in the universe. So do you have that animation of the stars going around?
I do. And actually I put it into the event page so all of our all the people attending can see. Here, screen share it real quick.
Okay. Okay. Yeah. So this is an animation, and this is from 2011, I think. But this is an animation of the stars in the vicinity of the galactic center, which is the galactic center is marked by that star shape. And these are all stars where we've measured the orbits, and we can see how close they're moving to the black hole and how quickly they're going. And so watch some of these. There's one called there's one coming in from the side that just whips right around.
Yeah,
it's black hole.
It's like this one right here.
Yeah, that guy, SO16. That goes really, really close and moves around really, really quickly. And then there's another one called SO2, which is the one that makes a kind of nice oval shape at the top.
Right.
I think that's the one that actually gets the closest, and that gives us our sort of closest limit of the the distance of how close those stars are getting. So one of the things we can do is we can measure from the orbits of all those stars how much mass has to be contained within that orbit for the star to be moving that fast, and plot those up for all of the different stars. And what we see is that at some point, all of the stars within a certain radius have the same amount of mass within that radius holding them in, and they just get really, really close. And so we can show that there's not some extended thing. It's not like a cloud. It actually is one thing, one object in the very center, and it's really, really, really small. So that's one of the indications we have. Another indication we have is the speed of variability of the black hole. When we see the flickering in the X-rays and stuff, we can get limits on the size based on how quickly it's varying, because there's sort of like the light travel time from one end of the black hole to the other.
Right.
It can't be too big, or else it wouldn't be able to vary that quickly in terms of the light.
So basically, what we're saying here is that, yes, they do exist, and we have a huge amount of evidence to support this.
Yeah.
I think this gets more into a prove to me that science works, and when we're talking about mathematical proofs as opposed to scientific proofs, and the words theory versus theory in scientific sense, this is what we're talking about. And so yes, there is a large amount of evidence to support that black holes exist.
Yeah.
There's really nothing else out there that could be doing what this is doing. We actually have run out of time. I did get a really good question from Twitter, and I think it's going to be a great one to follow up with. Maybe this is from Henna Khan. It says, do all dwarf galaxies have black holes in their center, or only larger ones? So I think that's maybe something we can look into in the future about what environments do black holes come in from. Is there anything you wanted to add before we have to go? Because we ran out of time. It goes so quickly.
That's really quickly. That went so much faster than I expected. Well, for the dwarf galaxy thing, we think we see some sort of intermediate mass black holes, but we're not really sure. That part is really uncertain, and we could get into that at another time. But yeah, I don't know what else to add. I don't know. There's just these things. Oh, so I guess the one thing I would want to add is that there's this idea of black holes being these sort of ruthless killers that go around and vacuum things up, right?
Right.
And it should be, you should note that you can orbit a black hole perfectly happily if you're far enough away, and it's only when you get within like a few times the Schwarzschild radius that you really have to worry, and that is a really small radius. So like for the black hole at the center of the galaxy, it's 40 light seconds. You have to get really close before you have to worry about it. If our sun turned into a black hole right now, unless we were a few kilometers away, gravitation...
Our orbit would be the same. It's the same amount of mass, right?
Yes, the same amount of mass. So our orbit would be fine. So really, black holes, they only eat things that come really close to them. They don't, they can't just go around vacuuming things up from all around the universe.
It's not the evil black holes going through the universe. It's it's this large amount of mass.
I think they're vilified a bit. The black holes are everywhere. They're ubiquitous. They're perfectly nice objects most of the time.
Right.
So I think we should recognize that they're just part of the universe, and they're just objects like any other objects. They're just you just don't want to get too close. All
right, space fans. So if there's any other graphic artists out there besides me, I want to see some awesome Black Holes Need Love 2 GIFs that are going around. If you do, send them to us over on Tumblr at spacefannews.com. Thank you all. I have a bunch of questions and comments. I will have to try to either address them later or use them as follow-up topics. But we've been having a lot of great questions and comments, so thank you all for them. And we'll try to break them up and do more explainers, or we'll put them up into Space Fan News package videos like we typically do. Paul, your beautiful images. Is it all right if I put them into the event page for people to see the full version of, or if you can put them in there?
Yep, not a problem.
That would be awesome. That way, so for those of you watching, this is Paul's image from New Zealand. How long did it take you to make this image?
That is 50 minutes worth of red, green, blue, and about 70 minutes worth of H alpha.
So each?
Each.
So, wow. So that's a little over 3 hours worth of data there.
Yeah.
This beautiful image just for you. This is for you guys, space fans. I did ask Paul to take an image of Sagittarius just for this show. So if you guys get a chance, please follow Paul at AstroStew on Twitter. Also, he's huge on Google Plus and shows out some amazing, phenomenal astrophotography. And Katie, thank you.
Yes.
This was a lot of fun.
Yeah, this was really good.
So we'll have to do more of these. Where can people find more about you and your awesome work?
Well, you can find me on Twitter at AstroKatie. I'm also on Facebook at facebook.com/AstroKatie. I'm on Google Plus at +Katie Mack. And I have a webpage, astrokatie.com, where you can find all the stuff that I do in terms of science communication. And there's a link to my research page from there, too, if you want to see the kind of stuff I work on, dark matter and things like that.
And I found out earlier before the show started that you were the subject of a PhD comic, which made you so much more cooler in my mind. So I will put the link to that on YouTube and Google+, because that just, like, nerd cred just went up. So that's awesome. Again, everyone, I'm Scott Lewis at Scientific Scott on Twitter. We are Space Fan News, so you can find us all over the place. Space Fan News on Twitter. We are so close to 2 million followers here on Google+, so thank you all for your huge support. If you like this and you want to see more of it, click subscribe on YouTube and see our other shows that we're putting out and our sister channel, Deep Astronomy. So thank you all for watching, and as always, keep looking up.
Thanks.